In this section, we talk about the quadratic reciprocity law. We begin by discussing the squares in a finite field with Q elements, where Q is the power of a prime number P. The main theorem of this section is the following. If P is equal to 2, namely the characteristic of this finite field is 2, then all elements in this finite field are squares. What do we mean by squares? We mean for any y in FQ, there exists x in FQ such that the square of x is equal to y. The proof is easy in view of our Frobenius endomorphism lemma. This lemma is on the page number 3 of Serre's book, which we talked about at the beginning of this lecture series. The Frobenius endomorphism from FQ to FQ, sending x to x squared, is injective. But this FQ is finite. So this forces this injection between two finite sets to be a bijection. And this means every element in FQ has a preimage for this Frobenius endomorphism. Namely, every element is a square of some element. And this proves the first part. This is the first part of the theorem. Now let's look at what happens when P is not equal to 2. When P is not equal to 2, then the squares in the multiplicity subgroup of FQ, namely FQ star, form a subgroup of index 2 in the multiplicity subgroup. And this subgroup is the kernel of the homomorphism sending x to q minus 1 divided by 2. And this x to the q minus 1 divided by 2 can only have two values. This guy can only be plus minus 1 in FQ. And one can also write this in some fancy language of exact sequence. We can say one has the following exact sequence. The first term is 1, followed by the squares in FQ star, and then FQ star, then plus minus 1 and 1. So the second part says this sequence is an exact sequence. Namely, the image of an arrow, a map here, is always equal to the kernel of the next arrow, next map. Now let's prove the part B. Let omega be an algebraic closure of FQ. Any element in FQ star must have a square root in this algebraic closure because of its algebraic closeness. So we pick y to be a square root of a given element in FQ star. Such y exists because omega is algebraically closed. And now we look at this equation and take the q minus 1 divided by 2th power of both sides. Here we have already used that p is not equal to 2. And because p is a prime not equal to 2, it must be an odd number. So any power of p is also an odd number. So q minus 1 is an even number. So this is an integer. So we can safely take the power. But this guy can only be plus minus 1. And let me explain why this is true. This is because x to the q minus 1 is always equal to 1. Because x, remember, x is in this multiplic subgroup of fq. And f sub q star is cyclic of order q minus 1. So in particular, the q minus 1's power of x must be 1. And how do we move from here to here? From here to here, we use that the quadratic equation z squared equal to 1 has at most 2 solutions in fq. And we already know that plus minus 1 squared is always equal to 1. Because p is not equal to 2, so plus 1 and negative 1 are two distinct elements. So the only possible choices for this guy are plus 1 and minus 1. And now we make a claim. Remember, when we pick this y is in the algebraic closure omega of fq. Now we claim that this x is a square in fq if and only if y is in fq star. So let me write a claim. One direction of this claim is trivial. This direction is trivial from our construction. Because if y is already in fq star, then because y squared is equal to x, that means x is really a square in fq. For the other direction, we need a little bit more thinking. If x is a square in fq, say x equals z squared, where z is in fq, then because x is not equal to 0 by our choice, so z is also non-zero. So this already implies that z is non-zero. And now we take the q minus 1 divided by 2th power of both sides. And the right hand side is just z to q minus 1. And now because z is non-zero, so z also lives in fq star, so its q minus 1's power must be equal to 1. Because this subgroup is of order q minus 1. Then what about the left hand side? The left hand side is precisely y to the q minus 1 from above. So this means if x is a square in fq, then y to the q minus 1 must be equal to 1, not minus 1. Remember, previously we concluded that y to the q minus 1 is equal to plus minus 1. Now, if x is a square, then this y to the q minus power must be precisely equal to 1. But what does this mean? What does it mean for y to the q minus 1 is equal to 1? If you remember our structure theorem for a multiply subgroup of a finite field, this precisely means that y has to be in fq star. Remember, at the very beginning we proved a theorem 1 on the structure of finite fields. And in the part 2 of the theorem, it says that there exists a unique subfield fq which has q elements, and those q elements are precisely the set of roots for the polynomial xq minus x. But now we are looking at fq star, the non-zero elements. So any y satisfying y to the q minus 1 must live in fq star. And this verifies the claim. And now we make another claim. We claim that the squares in fq star is precisely the kernel of this map, sending x to x to q minus 1 divided by 2, which is plus minus 1. This verifies the exactness of this sequence at this position, because this map is precisely this map, and this map is the inclusion map. This claim is easy to verify. Indeed, fq star squared is the image of the square map. And from here, we immediately see that the kernel of this map contains the image of this map, which is fq star squared. Because x squared, if you further take q minus 1 divided by 2's power, this is just x to the q minus 1, which is 1. Because x is the element in fq star. On the other hand, if x is such that x to q minus 1 divided by 2 is equal to 1, namely in the kernel, then by our discussion above, we know x to q minus 1 divided by 2 is always equal to some y to q minus 1's power. By our construction, we only know that y is in omega. However, if x to the q minus 1 divided by 2 is equal to plus 1, then y to the q minus 1's power is also equal to plus 1. And that forces this y be in fq star, not just the generic element in omega. But what does this mean? If y lives in fq star, then by our previous claim, x must be a square in fq. And this implies that x must live in the image of sigma 2. And therefore, the kernel of this must be equal to the image of sigma 2. And the image of sigma 2 is precisely fq star squared. So this verifies the second claim. There's another statement of the theorem we haven't proved yet, which is the first sentence actually. So now we are going to show that the squares of fq star form a subgroup of index 2 in FQ star. And we're going to write this as the third claim. This claim is also easy to verify. By theorem 2 on page 4, we know that FQ star, as the multiplic subgroup of the finite field FQ, is cyclic of order Q minus 1. So now we suppose this FQ star is generated by A, where the order of A is Q minus 1. Then we know that this FQ star squared, which is the image of this sigma 2 map, will be a subgroup generated by A squared. And this subgroup has precisely the index 2 in this group. And this verifies this claim. So we have verified the first sentence of the theorem, part B, and we have shown that this subgroup, is a kernel of this homomorphism, and we have shown the exactness of this sequence at this position. And now it remains to us to see that this sequence is also exact at this position and this position. That this sequence is exact at this position is trivial, because this map is the inclusion, and in particular, the kernel of this map is trivial, and the image of this map is also trivial. So it is exact here. Why it is exact here? The kernel for this map is plus minus 1, because this is a trivial map. Now it suffices to verify that this map is surjective. So why is this guy surjective? This is surjective because otherwise, if this map sends the whole group just to plus 1, then the image omits the negative 1 element. Then that means the kernel of this map will be the whole group. However, we have shown that this guy is a subgroup of index 2 in this guy. So this is not surjective, which means the kernel of this map cannot be the whole group. So this map must cover both plus 1 and minus 1. So this is also exact at this position. And this finishes the proof of the part B.